to introduce Leonid Polterovich from Tel Aviv, who will talk about approximate representations and quantization.
Okay, so thank you very much for the invitation. It's a great pleasure to be on this seminar. So I will talk about two joint works, one with Louis Jos and David Kazhdan, and another with Florent Charles, which deal with approximate representations. So let me recall the problem which goes back to Coulomb. So actually Coulomb formulated it in one of his talks in 1940, and the question sounds like, is any almost representation is a near representation, so close to a genuine representation? And the question turned out to be pretty interesting. So for instance, so let's say something kind of slightly more precise. So approximate representation of a group is mapped to unitary group, which satisfies f of x, f of y minus, f of xy is less than epsilon for every x and y. Yeah, so that's a type, f of x, f of y minus f of xy. Okay, and here one has the following theorem. So due to Grove, Karcher, and Drew in 74, so the answer is yes. So every almost representation is close to genuine representation if G is a compact Lie group. And there were various extensions of this result. So for instance, to amenable groups due to Kazhdan, to some finitely presented groups, but then this almost homomorphism condition should hold for kind of generators, let's say, due to De Schiffer, Glebsky, Lubotsky, and Tom. And but in general, it's not true. So the idea of this talk is the following: that quantization gives rise to almost representations of various algebras and groups. And Coulomb stability, which, for instance, in case of algebras seem to be kind of new, yields applications to quantizations and to Hamiltonian dynamics. So that will be kind of my point today. So let me start with Coulomb stability for algebras. First result deals with Lie algebra SU2. So it's generated by L1, L2, L3 with natural commutator relations. And I wish to remind that if we have a unitary and dimensional reducible representation, so some of the squares of these generators is with sign minus n square minus 1 over 4 times identity. And so here is the first result. So for every C in R, and little r positive, there exists sufficiently large K0 and a constant with the following properties. So now assume that we have a finite dimensional Hilbert space, and assume that we have a K natural and triple of operators Xi, which are skew Hermitian, so which satisfy the following conditions. So first of all, they almost satisfy this equality. Yeah, so equality for the sum of squares. So x1 square plus x2 square plus x3 square plus the strange number k square over 4 plus kc over 2 times the identity is less or equal than r. And second, this is an almost representation in the sense that xj plus 1 minus xj plus 2 in the operator norm is less or equal than r over k for every j from 1 to 3. Okay, and so first conclusion is that this number c is necessarily integer, and if dimension of H is less than 2 times K plus C, so then actually you have a kind of rigidity result, right? So dimension actually equals K plus C, and there exists a genuine irreducible representation SU2 to SUH such that Xj minus rho of Lj, remember that LJ generators in the operator's norm less or equal than C.
Sorry, Leonid, may I ask you?
Yes, yes, of course.
I get a little bit confused because in the beginning you're saying for every C in R, there exists this K naught. But then then C is in Z, like probably I'm misreading something, right?
Yeah, so formulation goes like this. So if C is not in Z, so simply such gadget does not exist. Okay, so the only possibility for these assumptions to be non-empty is C is integer, and so then this integer C actually plays an important role. So it enters into dimension of this.
But still, when you say for every C in R, there exists K naught in N.
So I'm saying, you see here is the keyword assume. Assume that, okay? So if C is not integer, so assumption is void. Okay, so that's.
Yeah, I have another question. Why do you bother with K naught and then K? Why not just choose K naught large enough so that you can use it as K?
Because this this is statement for all sufficiently large K. Okay, so in this or another.
So where you said there exists K, you mean for all K?
Yes, yes.
Oh, okay.
This is probably K0 and there is a typo, no?
What?
No, the typo is in the third line where it says there exists K, and what he said it should be is for all K.
Assume that there exists K with K is greater or equal. So again, it's this should be read as following. So I don't think there is a typo actually. So there exists K0 with the following property. So for every K, yeah, so assume that there exists K. So for every K for which this condition holds, automatically C is integer, dimension equals to K plus C, and
I see. Okay.
An actual representation.
Okay, I get it.
Yeah, so somehow I believe that formulation is precise. Maybe English is clumsy. I don't know, but so I decided to put this K0 kind of out of the statement. Yeah, and so then whenever we assume that this is true, so then we have this conclusion and this almost representation.
Okay.
So that's the statement. I also want to say that this operator xj are kind of large. Yeah. So their operator norms are of order k. So this kind of commutation condition is pretty sharp, and the fact that something is less or equal than constant is also surprising. Okay. So kind of funny thing in this story is that this coefficient at k, yeah, so plays a role. So it actually enters the dimension of the Hilbert space, and it makes all the story rigid. And the dimension assumption is needed because otherwise you can consider actually sum of two irreducible representations like and of dimension 2k, and so then then this you cannot approximate by the irreducible representation. So that's the story for SU2. So similar statement is for now let's pass from Lie algebras to C-star algebras. So consider quantum torus. So I view quantum torus as algebra generated by two elements W1, W2, which are unitary, and W1, W2 equals to in the power 2 pi theta W2, W1, theta is in S1. And here is a theorem. So again, with the same kind of, should be read in the same way, that if we know that xj star minus identity in operator norm is less or equal than r over k cube, and x1, x2 minus e in the power 2i pi over k plus c x2 plus x1 is also less or equal than r over k cube, and dimension is less than 2k plus c. So then we have c equals to z, dimension k plus c, and there exists a star representation with theta equals to 1 over k plus c, so that our rho of wj minus xj is of order capital O 1 over k in the power 3 over 2.
Leonid?
Yes?
I have a possibly stupid question, right? So there are all those like kind of magical powers, k cube, and on the previous slide there were some other powers. So you'll probably explain, right, how those powers come about, or?
Well, I will do the following thing. So I will rather explain some consequences of this result. So I will explain why we need these powers. Okay. So let's do the following thing. So in terms of proof, I plan to say a word. So here is okay. I can a little bit run ahead and say the following thing, that so original, for instance, statements about groups, yeah. So like theorem by Grove, Karheru, and Kazhdan. So was proved with some rather conceptual machinery. So in simple words, what you are doing, so you're trying to initiate some kind of Newton method. So this Newton method gives rise to homological equations. So you do some analysis in group cohomology and you solve the equation, you get the result. So unfortunately for algebras, so this method gives very bad estimates. So it also works. One can imitate method by okay, so let's say by Kazhdan, yeah, and get kind of some results which are not so useful if you wish to study quantization. Okay, and
so you mean that maybe you get some of these inequalities from an Nash-Moser argument?
Yeah, so I'm saying the following thing, that we got these inequalities in the following way. So for instance, in the case of Lie algebra, basically what you are doing, you are imitating the simple classification of reducible representations, but with estimates. So it's analysis, yeah. So it's I would say pretty complicated kind of solutions of quadratic inequalities. Okay, so we are just solving them and analyzing them, and you're getting the result. I don't know any conceptual proof of this result, and more conceptual methods gives worse results. So that's kind of the point. Okay, and so now let's do the following thing. So at least in this result, so we have some kind of dimension assumption. So we have assumption on Casimir and on almost representation, and we know that it is a near representation. And so now I will explain how this result can be used for study of quantizations. So here is the question which we address, but we address this question in the category of geometric quantization. So I'm using this term in a little bit extended sense. So it's geometric quantization as opposed to deformation quantization, to star product. So assume that we have a closed symplectic manifold, finite dimensional, and so I need a family of complex Hilbert spaces of finite dimensions and family of linear maps from real valued smooth functions to Hermitian operators, as usually so normalized so that TK1 is the identity, and extended to complex functions by C-linearity with three axioms. So norm correspondence, so operator norm of TK of F is almost the uniform norm with remainder capital O1 over K. So we have bracket correspondence. So TKF, TKG commutator is I over K, TK of Poisson bracket FG plus capital O of 1 over K square. And TKF times TKG is TK of FG plus 1 over K C1 of FG plus 1 over K square C2 of FG, let's say plus terms of higher order, where this C1, C2 are bidifferential operators. So I will also use that remainder. So these remainders, capital O's, they are defined in operator norm, and they uniform in certain amounts of derivatives of functions f and g. So crucially, they depend on functions f and g, since otherwise the object is kind of too good to be true. But this remainders depends on n derivatives of f and g, where n is large enough. I don't need much about this n here. Okay, and so this story started with the work of Butet-Emanuel Guillemin and the fundamental work of Boardman, Meinrankin, and Schlichenmeyer, who actually introduced this kind of study of the story in operator norms. In the Keller case, in case of Keller manifolds, and a lot of people worked on this problem for almost complex manifolds. Of course, there is condition that M is quantizable, so cohomology class of omega over 2 pi is integer. And so in this situation, such quantizations exist. And what I wish to address is the following questions. Question about semi-classical equivalence of quantization. So assume that we have Hilbert spaces HK and HK prime of the same dimension when K goes to infinity, H bar is, let's say, 1 over K. So I will say that two quantizations are M equivalent if there exists unitaries from one Hilbert space to another Hilbert space, depending on H bar, so that for every smooth function, second quantization is simply conjugate to the first quantization up to error of order H bar in the power M. So somehow I wish to understand when quantizations are equivalent up to order H bar in the power M. So equivalent means conjugate. And this problem makes sense at least when M is 1 or 2. So I cannot say anything intelligent about higher M. But for M equals to 1 or 2, so there is some story around. Okay, and so here is a theorem. So if M omega is S2 or T2, and we have geometric quantization with the lim sup K goes to infinity, HK over K is less than 2. So then there exists integer, so that for all large K, dimension HK equals to K plus M. And actually, any two quantizations with dimension HK equals to K plus M are one equivalent. So somehow in this axiomatic approach to quantization, so at least for sphere and torus, any two quantizations are one equivalent. And basically the proof goes through this Coulomb stability theorem, right? So for instance, for the sphere, you start with functions x1, x2, x3, so you get almost representation of Lie algebra as U2, and so then you approximate by actual representation, and so then you basically continue to work by using all these axioms. So basically this was original motivation which brought us to the solution of a certain problem, Coulomb type stability problem for Lie algebra SU2 in the case of sphere and quantum torus in the case of T2. So that's kind of answer to Anton's question, yeah. And so in order to do this, we need kind of pretty sharp remainders. Okay. So again, okay. So now the result is true for one equivalent. It's certainly wrong for two equivalents, because there is invariant which comes from C1 of Fg, and here I will be very brief. So let me impose two extra abstract properties on quantization. So first is positivity. So I want to look at kind of Berezin-Toeplitz quantizations, which send positive non-negative functions to non-negative operators, and reversibility, which means roughly speaking, that if you first quantize and then dequantize your function, you get original function plus capital O of h bar. And so then actually one can prove the following theorem, that if you consider, if you symmetrize this B-differential operator C1, so remember that C1 entered into this kind of axiom, so Tk of f times Tk of g equals to Tk fg plus 1 over k C1 of fg plus 1 over k square C2 of fg. So in principle, it would be absolutely reasonable to say that there exists a star product, so that we have asymptotic expansion Tk of f times Tk of g equals to Tk f star product of g. But I need for this story only first two terms. Okay, and probably for today I mainly need this first two terms. Okay, and so I'm saying the following thing, that from this C1 you can cook actually under these two assumptions a Riemannian metric. So like C1 of fg plus C1 of gf equals to minus g as grad of f as grad of g, where g is a Riemannian metric. And moreover, this metric turns out to be compatible with certain almost complex structure, yeah, which did not appear in the original formulation. So there was no almost complex structure in the story. And volume of M volume of mg is always greater or equal than symplectic volume, and equality means that actually g comes from complex structure. So g equals to omega of cj eta.
So, sorry, Leonid, I probably just missed. So you require this symmetrization of C1 to be non-degenerate, or it just always...
No, I'm saying the following thing, that if I have this positivity and reversibility, so then this symmetrization is always non-degenerate. And actually, it's not just non-degenerate. It actually, I mean, have the following form. Yeah, I didn't write this here, but okay, let me tell this. It's a compatible metric plus non-negative extra. Okay. And so then you have this volume inequality, and equality means, so minimal possible volume of such metric is a symplectic volume. And it is symplectic volume if it's actually a compatible almost complex structure. Like, I mean, symplectic topologists work with. Yeah. Actually, this metric has some quantum mechanical meaning, and this statement is called least unsharpness principle. But I will probably I will skip this discussion. I want to go into different direction. I just want to say the following thing, that this metric is certainly invariant of two equivalents for like positive reversible almost complex quantizations, and one can, but however, one can prove the following thing, that let's impose the following condition. So we want to consider positive reversible equivariant quantization. So let's impose equivariance condition. And if we impose equivariance condition, so then actually this unsharpness metric is a complete invariant of up to two equivalents. Okay, so that's the statement. So as you see, we okay. I want to show you some slides. So this slide is I don't know. I like it, and then I will simply show you it. Okay, so consider the following kind of range of quantization. So let's assume that dimension of hk equals to k plus m, so m is integer, and I'm doing the following thing. I'm taking standard Berezin-Toeplitz quantization with index k plus m minus 1, and I'm applying it to the following thing. So I'm applying it to image of f under heap kernel. So somehow in the language of, if you wish, quantum measurements, yeah, and of course, I mean, quantization, positive Berezin-Toeplitz quantization is given by positive value, operator valued measure. So it's kind of main object of quantum measurement. So you can do the following thing. You can take Berezin-Toeplitz quantization and smear it, diffuse it by diffusion, okay? And so then you get certain quantization. And you can all, of course, I mean, this is good for positive t. So for negative t, well, you lose positivity, so you can go in the opposite dimension. But of course, I mean, kind of, let's consider just one term in the asymptotics. Okay, you lose positivity, of course. It's kind of anti-diffusion. And so then you have the following scale, right? So you have a family of equivariant quantizations on the sphere. Yeah, so t equals to 0 corresponds to Berezin templates, and kind of positive t, you get these diffused Berezin templates. And in the negative direction, you have some remarkable values of the parameter. So t equals to -1/4, it's metaplectic constant Surya, which together with, let's say, C1 equals to 0, it gives you best possible quasi-multiplicativity. It's a kind of fine quantization, so with very good remainders. And also, if m equals to 0, it has best bracket correspondence. And for t equals to -2, it's constant Surya, it has best norm correspondence. So somehow this is the scale of equivariant quantizations of S2, which are determined by their kind of unsharpness metrics, at least in this positive part. Okay, and so they have some remarkable properties. So these are examples, if you wish. Okay, so as I said, so proof of stability is just textbook classifications with estimates. And my question is, does there exist a conceptual proof? So we have dimension assumption, which dimension of HK of FK lim sup less than 2 cannot be relaxed or not for this classification story. And there is actually the following conjecture. So any two geometric quantizations in my definition of a closed symplectic manifold with sequences of Hilbert spaces of the same dimension are one equivalent. Okay, and actually there is a remarkable result by Laurent Charles, actually more than a decade ago. He proved that this is true for Kähler quantizations and most probably true for almost Kähler quantizations, but how to attack such a result axiomatically is not clear. And for instance, extension of our stability theorem, like for general compact Lie algebras, should yield with some probably extra work affirmative answer for coadjoint orbits. But the problem is that, as I said, so our proof is very much down to earth, and actually generalizations to already, I would say, SU3 is, I mean, seems to be complicated. Yeah, so that's basically the end of the second part of the story which I wanted to tell you. Okay, so let me, I mean, any questions, because it's probably a good moment to ask questions.
Yeah, I have a sort of complex, oh, I can't start my video, sorry. I have a complex, oh, there we go. I have a complex of questions I'd like to ask, because somehow Kähler quantization involves the choice of a polarization, but there's this much more agnostic type of quantization, like Weil quantization, where you avoid all discussions of polarization. And so I wondered how that correlates to that zoo that you drew on an earlier slide.
So, okay.
I mean, you haven't, I mean, let me just say, the one name you haven't mentioned is Homander. And I'd like to, you know, Homander, of course, wrote a lot about Weil quantization and its special role.
Well, so once again, polarization enters into the positive story. So if you have positivity, so then simple axioms guarantee existence of canonical almost complex structure associated to the story. And okay, positivity and reversibility, but without reversibility, I basically refuse to think about quantization. So you want to hope for good. So if you quantize, you in first approximation get the original observable, right? Okay, and so then you get this almost complex structure, which is natural. And then there is in principle chance to kind of to reconstruct this quantization. So now for negative quantization, so I'm not sure what to do. So there is some room for doing changes of variables to which we will arrive now, which are kind of more formal. Okay, and so then maybe we can arrive to something positive. But I don't know what to say about it.
Because nevertheless, I mean, the Val quantization really doesn't incorporate any sort of polarization in its description.
Yeah.
And I think it's my impression that it has the best error estimates in the classical pseudo-differential calculus.
Yes, but the point is the following: that while quantization, you can I mean, when you are trying to insert it to the manifold kind of, yeah, so then you have to compromise to the closed manifold, let's say. Okay.
Yeah.
Yes, and so okay, so now I understand maybe what you asked. So interestingly, so there was a work by Gerchenstaber. So this kind of famous guy from Deformations of Algebras, who wrote an article of, I would say, kind of physical flavor, trying to also to ask what is the optimal quantization. And it actually somehow is, I would say, it's different from what we did, because he is working on R2N, and he comes to the conclusion that probably Weyl quantization is the best. Yeah, but at least he tried to find a way to ask this question.
Right.
Okay, and the way to ask this question from physical perspective is the following: that basically errors of quantizations can be interpreted as certain increments of variances. Kind of, yeah. So when you quantize a function, you get observable, yeah, and so you can consider it a phenomenon observable with its own variance, or you can consider it still as a kind of classical observable, right? So then you have a variable with respect to Husimi measure, and so on. So variance, the idea is that under quantization, variances grow, kind of. And Gerchenstaber was aimed at kind of finding with quantizations with minimal increment of variances, and that's more or less what kind
About which year roughly is this publication you mentioned?
It's actually, I think, 2000 something. So
Okay.
it's late, kind of.
Yeah.
Right.
Okay. Thank you so much. Okay.
Yeah, you're welcome. Yeah. Okay. So let me. Right. So I spent half an hour. So okay. So let me. Maybe I will be brief here, but I'm reluctant not to talk about it. So okay. So there is another quantization, which is deformation quantization, right? So and introduced by Bain, Flatov, Frontland, Lichnerovich, and Sternheimer. And the star product axiom for geometric quantization would be on the level of asymptotic expansion, TKF times TKG equals to TKF star G. And here I wish to also bring into discussion kind of formal changes of variables. So changes of variables of the kind f goes to f plus sum over m h bar in the power m am of m, where am's are differential operators. And so locally in a neighborhood, by change of variables, we can achieve that C1 plus and C2 minus. So by the way, C2 minus is anti-symmetric part of C2, is indeed Mayel-Weil. But globally, let's say in dimension 2, you can in principle achieve that C1 plus equals to 0 and C2 minus of Fg equals to IC Poisson bracket of Fg. And this is basically which appears in a work by Good and Ronsley, and this is also kind of used for one equivalence. Okay, so now canonical trace. So as we said, locally in a disk, let's say star products are equivalent to Mayel-Weil with C1 plus equal to C2 minus equals to 0 by certain change of variables, and so we can introduce trace. as a map from smooth functions extended by h bar to numbers extended by h bar, so that for each f supported in this chart is just integral over x au of f d volume to ph bar in the power minus d. Okay, and that's it was introduced by Nest and Tsigan in '95, and I would say that it is a somewhat mysterious kind of object, at least for me. And on the other hand, there is a down-to-earth approach to trace. You can simply quantize if you have geometric quantization, and you can, well, just take trace, yeah? And so then we impose another axiom, which is trace axiom, that tk of f equals to integral of mf rk times volume, yeah, so that you have kind of smooth density, and for this smooth density with normalization which I have, rk is 1 plus k in the power minus 1 r plus higher order terms. And our result with Louis and David Kazhdan is that for sphere or torus, if we have geometric quantization which satisfies star product axiom and trace axiom, and dimension of each k equals to k plus c, so then for every f in C infinity of m, we have asymptotic expansion. Actually, we have equality trace tk of f equals to this canonical trace plus capital O 1 over k. Okay, and so these two notions of trace coincide, and the point is the following. So one can show that after this change of variables, C1 plus equals to 0 and C2 minus equals to minus C over 2 Poisson bracket Fg. So that's basically this Guth-Ronsley formula, but with C is exactly the same C which enters into this dimension shift. And if you remember, it entered into the coefficient at k in the expression for Casimir. Okay, and so then you can also achieve that this function R is constant, and so then some calculations, separate calculations of trace and canonical trace actually give these two equalities. But this equality, so the fact that here we get the dimension shift, uses the stability theorem under our assumption. So that's another application of stability to quantization. Okay, and so again, for Kähler quantizations, it was known before. It was done by Hawkins in year 2000. Okay, so let me sum up maybe very briefly what I said so far. So I said the following thing, that we have this Coulomb stability for two very simple algebras, for Lie algebra SU2 and for quantum torus. And we have two applications. So one to equivalence of applications, which allows axiomatically get certain results which were proved in Kähler case by Laurent Char, and also we can establish equality of two kinds of traces, so trace in the quantization and canonical trace coming from star product. Again, in Kähler case, this was known by Hawkins earlier. So somehow this Coulomb stability kind of result is helpful for proving certain statements about the quantization. Okay, so that's basically the first three parts of the story, and so now there will be the fourth part, which is a little bit longer, and while previous results were based on joint work, or maybe two joint works with Louis Jos and David Kazhdan, so this is a joint work with Laurent Char. Okay, and here I'm entering even kind of less comfortable waters for me, but I will try. So first of all, we need this notion of Shatton norm on operators. Yeah, so you consider square root of A star A in the power p, then take trace and consider power 1 over p. So it's certain norm for p equals to 2 is just standard kind of L2 norm on operators. And I will denote by PUH projectivization of unitary group, and delta p the correspondence distance corresponding to this Shetland norm. Okay, and so here comes definition. So it's a clever definition due to Deschifre, Glebsky, Lubotsky, and Tom, recent. So it's a kind of activity in this direction goes on this day. The only thing is that they mostly worked with kind of unitary representation. So we need projectivize by some reasons, which will be clear later. And we use by their terminology, we say that the group gamma is p-norm projectively approximated if there exists a sequence of maps from gamma to this projectivization of projective unitary group of Hilbert space of growing dimension, actually, so that in the limit distance between rho k of x, rho k of y, rho k of xy is 0. So you see it's kind of almost representation, if you wish. It's object very close to the one I considered. And it's faithful in the sense that limit of delta p rho k of x identity is positive for every x which is not the identity. Okay, so again, it could be that in huge amount, kind of finite amount of groups you get to the identity, but then eventually it becomes kind of disjoint from the identity. And a theorem by Lubotsky and Oppenheim states that for every p between y and plus infinity, there exists finitely presented non-p-norm projectively approximated groups. So it's a difficult statement, and cases, I believe, 1 and infinity are open, and probably infinity, which corresponds to operator norm, is actually a big open problem. And the groups are complicated. So so groups are certain finite central extensions of lattices in simple L-adic Lie groups. So one can write down absolutely concrete group, but I don't know if this will be actually a relief. So ID is beautiful. So first you take such a lattice and you take such an extension so that the group is not residually finite. And then it turns out that by analyzing cohomology of these groups, you prove that this group is Coulomb stable for almost representation to certain ultra limit of these projective unitary groups. And so then you get that the group is residually linear and not residually finite, and that's contradiction with some Maltsev theorem from group theory. So somehow you prove stability, so then from stability you prove kind of residual linearity. So this means that every element could be sent kind of non-trivially into some linear group. Okay, and so then it's contradiction with another property which exists kind of independently of this story, being not residually finite. And here is what I can say about this. I mean, what we can contribute with Laurent to this discussion. So assume that we have a closed Kähler manifold, quantizable, and here is an assumption that C1 of Tm is even on kernel of omega. Okay, it's some kind of slight generalization of metaplectic situation. Okay, and the examples are, for instance, projective spaces or real surfaces. And here is theorem that if P is greater or equal than, okay, so that's, again, misprint, greater or equal than D, so gamma from omega is P norm projectively approximated. So for sufficiently large P, gamma from omega admits such a almost representation, which is here. Okay, and you see it's a funny story because basically it's not true for some nice, I mean, unless you are on the surface, so it's not true for some user-friendly norm, like with p equal to 2. On the other hand, when p equals to infinity, such a result does not seem to be tremendously useful, because potentially at least every group is kind of operator norm projectively approximated. But this is a restriction on a group. And as a corollary, there exists non-p-norm projectively approximated groups which do not admit, actually finitely presented, right, which do not admit a faithful Hamiltonian action on m to n omega. And for instance, you simply take this lattice, which exists in Lubotsky-Oppenheim story, and you conclude that it cannot act faithfully in a Hamiltonian manner. Okay, so again, I'm sorry, so there is discrepancy for dimension n and d, so we remember that n is the same as d. So some motivation for such results come from, for instance, Zimmer program. So Zimmer came up long ago with powerful program which asks which finitely generated groups or finitely presented groups can act on manifolds of kind of small dimension. And there were, he asked specific question about lattices, though probably not in periodic Lie groups, but in usual Lie groups. And recently there was a big progress due to Fisher, Hurtado, and Brown in this direction. So however, it seems that their work does not touch so far kind of Eliadic lattices. And so, for instance, this gives a constraint on action of certain groups interesting to certain community. But I think that what is interesting to me in this story is that the proof is based on quantization, and so that's what I want to explain. Okay, so we will forget all this kind of fancy finitely presented groups. So what we want to do, we want to build a faithful asymptotic projective representation of this group of Hamiltonian diffeomorphisms, actually. So that's what we want to do. Okay, so and for this purpose we need the notion of fine quantization. So it goes basically exactly in the same manner as definitions before. We have certain sequence of Planck constants which are slightly differ from 1 over k, but not much. Finite dimensional Hilbert spaces, linear operators. So I kind of by purpose denote them by qk, because this is not kind of Berezin-Toeplitz quantization, it's little twist. And here are the properties. So we want norm correspondence, we want dimension formula, and the main kind of point is that we want to have bracket correspondence with especially small remainder. So remainder in bracket correspondence should be 1 over k cube, of order 1 over k cube. Otherwise, I mean, this simply will not work. So as opposed to usual capital O 1 over k squared. And what one can prove that if you have a closed symplectic manifold, so dimension 2n, quantizable, and assume, so you have this assumption spade suit C1 of Tm is even on kernel of omega, so then M admits a fine quantization. So that's basically the statement. And so how one proves this? So it's proof really is based on a work of Laurent Charles of 2007. So you just first start with Berezin-Toeplitz quantization for L in the power k times E, where L is pre-quantum bundle and E is defined as follows. So you choose class E so that half of Chern class minus lambda C1 of L is integral, so it's equivalent. It's easy to see that it's equivalent to this evenness condition of first Chern class in K of omega. And so then you simply choose E with C1 of E equals to E, and you change a little bit Planck constant. So now hk is k plus lambda in the power -1. And you denote qk of f to be tk of f minus 1 over 4k Laplacian of f. So if you remember this my kind of diagram, right? So this is more or less cousin of metaplectic constant Fourier, which has best bracket correspondence. And so that's exactly what we want to have here. Okay, so that's construction of such a quantization. And so then you do a simple thing actually. So you quantize symplectomorphisms in the following way. So let ft be a Hamiltonian function generating Hamiltonian flow phi t, and phi is in the group of Hamiltonian diffeomorphisms. So I will denote by ham tilde from omega universal cover. And what I'm doing, I'm simply looking at Schrödinger equation with quantized Hamiltonian, where the quantization of Hamiltonian actually comes from this fine quantization. So I probably have to say that Hamiltonian, I mean, to have it kind of unique, I want to normalize it by zero mean. It will not be much important. Okay, but let's do it. And so then you get unitary operator. So you to every actually path of Hamiltonian diffeomorphisms, you have a unitary operator. And thus you have a family of maps from universal cover of Hamiltonian group to unitary group, which sends lift of Hamiltonian diffeomorphisms to unitary operator. And of course, it depends on choice of Hamiltonian path, joining identity with phi. Okay, and I will focus now, I will somehow split this dependence into two issues. So first of all, I mean, actually it depends on path alive, yeah? In the homotopy class, so this is serious problem, right? So and then there is dependence on homotopy class, so that's exactly what will be settled in a little bit later. Okay, so then here is our theorem with Laurent that if mu k comes from fine quantization, so then unitaries mu k of phi tilde and mu k prime of phi tilde defined via two choices of paths, homotopic with fixed endpoints and representing the same element in the universal cover, so they basically differ by capital O1 over k in the operator norm. And here actually we use this fine quantization. So the answer will be capital O of 1 for usual quantization, and this would be completely useless. Okay, and so then moreover this map satisfies this almost homomorphism property. Okay, but then the problem is that all right, sorry. Okay, and so there is third property that this is basically faithful. So if my phi tilde is not a loop coming from identity to itself, or phi is not the identity, so then this norm is actually quite big. Okay, and so let me say a couple of words about the proof. So proof of 1 and 2 is just Yegorov theorem, right? So kind of comparison between quantum propagation and classical propagation, but you should kind of take care of remainders. And idea of 3 is comes from symplectic topology actually, yeah. So the best way in symplectic topology to say that you have a Hamiltonian diffeomorphism which is not the identity is to say that it displaces some open set. And so if it displaces some open set, so then if you take whatever this means, a quantum state concentrated in this open set, so then this UK almost orthogonalizes the state. So hence comes 1/2. Okay. And now you see what about p-norm approximation? So you have an equality between operator norm and Schatten P norm with dimension entering there. So actually what enters is dk in the power p. And so dimension is of order k in the power n, and remainders here are of order 1 over k. So if p is large, yeah, so then somehow this remainders times the multiple which comes from the dimension still goes to 0. Okay, and so there you go. So you get fine quantization of universal cover of Hamiltonian group, and actually for this I don't need the term scalar. So scalarness comes into the play when one considers effect of loops. Okay, and so what one does with loops, so let me remind that if you have a loop of Hamiltonian theorem, of Hamiltonian diffeomorphism, so then all orbits are contractible. So amazingly, this result, that's true for any closed symplectic manifold, and this is consequence of Floer theory. So it's not a soft result, amazingly. Okay, so then if you have such an orbit, you can span it by disk, and you can do the following. So you can consider mixed action Maslov diffeomorphism. So you can consider symplectic action of such orbit and subtract with certain multiple the Maslov class. And if the constants are chosen in a clever way, so this does not depend on the disk. Okay, so it's some combination of what Alan Weinstein did in '89, and I looked at this, introduced this combination, which actually has real values in '97 for a study of Hofer's lengths of loops of Hamiltonian diffeomorphism. So anyway, we get such an invariant. And so then there exists a theorem that in Kähler case, unitary corresponding to a loop is basically a scalar operator plus a weight. And this is a difficult theorem, but hard work is done not by us. I mean, it's done in a work by very recent work by Laurent Charles and Johann Le Floch, who wrote an article about kind of sharp quantum propagation, and in particular, it's powerful enough to capture these results. And so this means that the effect of the loops is that you basically pay by scalar. So you end up with a projective asymptotic representation. So let me conclude. So that's that's basically the end of the story. So in this way you get projective asymptotic representation of GAM, and you can address a question about uniqueness of quantization. So somehow we forgot to do this in the paper.
Can I ask a question about the proof that you've done so far?
Yes, yes.
Here you are assuming that it's even because you are using the proof of Schall at the beginning of your proof. You're assuming that the first term class, it's even.
No. Yeah, well,
Yeah.
yes, but not this Schall, it's previous Schall. So you.
Oh, yeah, exactly, at the beginning.
Yes, you need.
So exactly, this theorem.
Yes, and
so you need it. I mean, to have finite quantization, you need this condition or not? The assumption. Do you have any counterexample?
No, it actually would be very interesting. I think it's an interesting question. So somehow again, it's this I don't know. Also, it is known that in Kähler case it cannot be capital O1 over k in the power 4. So that's sharps. But in axiomatic way, if you start arguing axiomatically, as we did during all the talk, yeah. So for me, Kähler was mostly an example. So only at the end I used kind of Kähler significantly, and probably even that can be removed. But okay, let's say it's the last result of Charles and Le Floch is proved in Kähler case.
Yeah.
Okay, but I absolutely don't know how to prove that 1 over k cube is the best kind of remainder for fine quantization. So of course, in positive case, you cannot have such things. So for Berezin-Toeplitz case, I think we did some analysis with Laurent in earlier work. Okay, but in general, maybe I mean maybe I cannot imagine it, but this is interesting open question. But another question which I want to, okay, I answered probably, yeah?
Yes, sorry, because I saw again the condition of evenness now in the uniqueness, and I was like, I wanted to ask this question before, and I didn't. Yeah, you answered my question. Thank you.
Yes, but in uniqueness, the situation is, as I said, is not very kind of satisfactory because we missed the question, and I started to ask it only when Anton invited me to give this talk. So what we can say about uniqueness is the following. So let's fix the following data. We fix pre-quantization Hermitian complex line bundle. It's not yet holomorphic with connection, but connection respects omega, and half form complex line bundle E so that E square is this lambda in the power n T star. So then varying complex structures on M, we get projective representation, projective representations mu J of Ham. Okay, I want to warn you that we did not write anything. So there could be kind of bugs here and there, but I believe that the following is true. So let's say this is a claim which sounds reliable to me, that it follows from Charles from 2007 that with all this data fixed, all these representations are conjugate up to capital O of H bar. So it's basically a canonical object. So now you can ask how this representation depends on this data. So is there uniqueness beyond metaplectic case? So no, sorry, Eva. So here condition is stronger. So we had condition that C1 of Tn is
this is a stronger
omega. This is stronger. So uniqueness beyond metaplectic case, extension to almost complex case, it's all work in progress. So I don't know, I even think that answers could be kind of complicated. So sometimes yes, sometimes no, but I quite believe that you have, so to say, finite dimensional moduli space of these representations. Okay, maybe it's too kind of brave, courageous kind of statement, but that's at least some hope, yeah. Okay, and the last remark is that about this Lubotsky-Eppinghaim group, so they are kind of complicated. So we, for instance, don't know whether they can act in volume preserving manner. So of course, according to the rules of this kind of finitely presented groups actions game, yeah. So if you rule out Hamiltonian actions, so you first ask the question, is it kind of hard or soft, and does there exist a volume preserving action? We don't know, and we don't know whether the asymptotic projective representation of Ham yield further abstractions and actions of finitely presented groups. So in principle it could be, but that's open. And I will stop here. Thank you very much.
Thanks a lot for this complete and nice talk from groups to quantization. Let's thank Leonid. So now time for questions. We have a question from Michel Semenov that maybe you want to unmute yourself or you want me to ask the question. Michel? I don't see him.
Okay, so I can read the question.
Yeah, it's on the. Yeah. I don't see him. Well, maybe he doesn't have a microphone.
A physical question possibly related to the notion of approximate representations. One note that the group of canonical transformations in classical mechanics cannot be quantized. Does it admit an approximate quantization with some qualified degree of accuracy? Okay, sure. So in a sense, this was the main motivation, and this result about approximate projective representation was motivated by this question.
Okay.
Yeah. So this was physical motivation for this.
Okay. Okay. Do we have more questions? I don't see hands raised. You can raise your hand or you can unmute and go ahead. I don't see raised hands now in the list. Maybe Nikita, maybe I am not good enough, but I don't see them. Any other question? Nikita, do you see questions? I don't see questions.
Nope.
In YouTube, I see 2 likes and 6 people have been following via YouTube.
I have a question.
Alejandro,
Yes.
you don't have your dog today.
No.
You can ask your question.
Yes, it might be a bit of a stretch, but is there any way of relating these results in which the Hilbert spaces are finite to other values of H bar where the Hilbert spaces are not finite dimensional?
Okay, so where Hilbert spaces are not for finite dimensional.
Yeah, it would be not the discrete.
No, you see, okay, so let's put it in the following way. So my understanding is that if you have a manifold of finite volume, so then for given H bar, you basically has one dimension per quantum cell. Okay, so then you get finite dimensional spaces, but of course, when H bar goes to 0, dimension goes to infinity. So in order to have kind of, at least from quantum mechanical viewpoint, meaningful infinite dimensional spaces, you need manifolds of infinite volume. And I think I personally worked on one example, which is Bargman space, simply R2N, where with Laurent we analyzed kind of remainders. So we were interested in remainders in this example. And there we more or less understand what's going on. Namely, so if you, for instance, have Hamiltonians supported in a given ball, yeah, of big radius, so then even though your operators are infinite dimensional, so but you can reduce them to finite dimensional. You could basically throw most of the dimensions to the junk. But if manifold is more complicated when your symbols are not completely supported, so I think there is this is a difficult question, and there is some literature about for instance, asking when the Stioplitz operators are of I don't know, trace class or something like this, and this seems to be a jungle. So analytically hard questions.
Ah, I see. Okay, thank you.
Okay, more questions? I have a question, but somebody has another question. Michelle, do you have a question? You look like you want to ask something. Simon and Michelle. Okay. I have a question. In your slide number 15, in which you have your result with yours, I mean, and Kasdan, and you do this for the sphere and the torus?
Yes.
And then you obtain the same, let's say, if I understood this well, you generalize like some result of Hawkins for Kellerverse in Teplitz quantization. You can only have this for the sphere of the torus, or did you try to do this more general, or is it impossible, or did you think about this?
No, we cannot do anything more than we did. So
okay.
So the point is the following, that one can, okay, so there are kind of two possible directions. So first direction is to go to surfaces of higher genus, which I would say we failed. So we discussed quite a lot with David and with Louis, and I don't know what to say. Seems to be complicated. Okay, so another direction which I think is doable, and even kind of for some simple Lie groups, like SU3, for instance, yeah, so Lie algebra, so SU3. I asked Utshapta, a student of mine, to look at this. So let me show the slide. So right. So we want to say that extension of stability theorem to general compact Lie algebras would yield affirmative answer for coadjoint orbits. And, I mean, for instance, if one succeeds to generalize the original stability theorem from SU2 to SU3, so you will get more manifolds for which our approach works. At at least there is kind of good hope to get this. Okay, but again, because our proof was very close to this kind of classification from the textbook with estimates.
Okay.
So doing this, at least starting this work now for more complicated algebra, look for me as a nightmare. So
Okay.
so that's what.
That's the motivation. Okay. Thank you. Okay. Thanks a lot. This was quite intense talk. We will probably need the slides, and Nikita, you can send the slides. All of us probably want to have the slides to follow it again. We will have it on YouTube. We can watch it as many times. But if you can send the slides to Nikita or to me or to Anton, we can put it online, and this can be very useful, I think.
Absolutely, I will do it.
Okay. So let's thank Leonid again for this nice, very nice talk.
Thank you very much. It was a pleasure.
So next week we have Luca Vitaliano. We have the title today. We got it in the email. I got it here. Who's gonna talk next week on Thursday? I had it here.
Calculus up to how much beyond the space of solutions of a PDE.
Of a PDE. So this is a completely different twist in Poisson geometry. I'm looking forward also to the talk next week. So I'll see you. We will see you. We will all meet here again, 5:15. Now I think all the times have been adjusted around the world. So I hope that for China, this is not too bad now. What time is in China now, Tudor? Tudor, we don't hear you.
1:30.
Oh my God.
Oi.
Of course, because China doesn't, I forgot, China doesn't believe in the change of time. I forgot about it. Okay. We need to rethink then about this. We need to, yeah, it's too late. It's definitely too late. We maybe need to shift it, but then it's too early for Alan. I don't know. It's like, it's very hard. We need to keep on the discussion. Yeah. Okay, so Leonid, thanks a lot for your talk, and I'll see you all here next week on Thursday.
Okay, bye.
Bye bye.
Bye, everyone.
Bye, everybody.
Bye.